Electron gas in metals. In metals, there are a large number of electrons which contributes towards conductivity, but they are not free to move out of the metal. They are constrained to remain within the metal, and these electrons are very much compressed. That is, it is having a high density. The electron density, the free electron density of metals is very high, and the electrons are light particles. So the particles are light, and the density of free electrons in metals is very large. And we know that electrons are fermions. Therefore, since they are light and the density is very large, they can be considered as degenerate Fermi gas. The electron gas in metals have the qualifications to be a degenerate fermionic gas, Fermi-Dirac gas. Degenerate Fermi-Dirac gas in the condition the particle should be light, the density should be large, and the temperature should be low. So at low temperature, this electron gas in metals form degenerate Fermi-Dirac gas. And remember, S is equal to half for electron. That is the degeneracy factor, which is 2s plus 1. That's equal to 2 into half plus 1. That is 2 in the case of electrons. But GS എന്ന് പറയുന്നത് 2 ആണ് ഇലക്ട്രോണിൻ്റെ കേസിൽ. And we have already derived the expression for Fermi energy at absolute zero as h square by 2m 3n by 4 pi v into gs. Electron case gs 2 ആണ്, so 4 into 2, that is 8 pi v 2 by 3, and this is the EF0 for electron gas in metals. EF0 equation we already derive ചെയ്തതാണ്. The only difference is that gs is 2 here. And substituting all the constants, എല്ലാ കോൺസ്റ്റൻസും substitute ചെയ്താൽ the energy will be 39 density rho raised to 2 by 3 in units of EV, and that is the EF0 in the case of electron gas in metals. And then Fermi temperature, the temperature equivalent of this energy, Fermi temperature is EF0 by K. KTF is EF0 and TF is EF0 by K. And again, substituting all the constants, we have already calculated the value for EF0. And here in the case of metals, the EF0 by K or TF is 10 raised to 5 Kelvin. And that is the Fermi temperature in the case of electron gas. Again, let's derive A, that is the degeneracy factor A in the case of electron gas, and particularly at low temperature. Any degeneracy factor എന്താണെന്നാണ് നോക്കുന്നത് ഇലക്ട്രോൺ ഗ്യാസിൻ്റെ കേസിൽ. particularly the temperature is low temperature situationലുള്ള value. We already know the expression for an approximate expression for A, the degeneracy factor, as 1 by gs n by v h cube by 2 pi m kt raised to 3 by 2. 2 pi m kt raised to 3 by 2. That is the value for approximate value for the degeneracy factor A. And let's see what is the value of A when t tends to 0. When t tends to 0, t is in the denominator. So when t tends to 0, A tends to infinity. The degeneracy factor tends to infinity. And in this situation, 1 by e raised to alpha plus x plus 1, that will be equal to 1 by e raised to alpha is 1 by a. 1 by a e raised to x plus 1, and when a is infinity, 1 by a is 0, so 0 into e raised to x, there is 0, 1 by, then this is 1 by 1, that's equal to 1. And this factor, that means this factor tends to 1 at this condition, when temperature tends to 0 and a tends to infinity, this factor tends to 1. And now we are going to derive an expression for A at the low temperature situation in the case of electron gas. And the expression for N is Gs V by H cube 2 pi m kt raised to 3 by 2 2 by root pi 0 to infinity x raised to half dx. And Gs is 2 in the case of electron, and this will be equal to 4v by root pi 2 pi m kt raised to 3 by 2 by h cube, and this is, the limit is from 0 to infinity. Here we know at low temperature, when t tends to 0, a tends to infinity, so we can replace this upper limit by a, 0 to a x raised to half dx, and therefore n is equal to 4b by root pi 2 pi m kt raised to 3 by 2 by h cube x raised to 3 by 2 by 3 by 2, and substituting the limits, this will be a raised to 3 by 2 by 3 by 2. Then we can rearrange, and we will be getting an expression for a as h square by, here expression rearrange cheyidal, this will be the expression for a 3n by 8 by v raised to 2 by 3, and this is the expression for degeneracy factor at low temperature. The temperature range is low temperature. ഇതാണ് ഇലക്ട്രോൺ ഗ്യാസിൻ്റെ കേസിലെ ലോ ടെമ്പറേച്ചർ സിറ്റുവേഷനിലെ ഡീജനറസി ഫാക്ടർ. And on substituting all the constants for electron gas, A for electron gas is found to be A is equal to 4.66 into 10 raised to 5 by T. That is a value for A. For electron gas, then when the temperature is low, it can be in a strongly degenerate case. When the density is very much larger, that is, it can be strongly degenerate at very low temperature. Strongly degenerate Fermi gas, we know there is the 0 point energy E0 and the 0 point pressure P0. And we already derived the expression for E0 and P0. The difference is that here GS is equal to 2. Degeneracy ഇവിടെ GS 2 ആണ്. Spin degeneracy factor 2 ആണ്. That is the only difference. And then we can also find the expression for CV at low temperature. CV is dou E by dou T at constant volume, and this is equal to dou by dou T of Fermi-Dirac gas in the case very low temperature. At very low temperature, the expression for energy is 3 by 5 N EF0 into 1 plus 5 by 12 pi kT by EF0 the whole square. There is the energy for strongly degenerate Fermi-Dirac gas at very low temperature. Absolute zero അല്ലാത്ത ലോഡ്, അബ്സല്യൂട്ട് സീറോ എപ്പോഴും ഒരു സ്പെഷ്യൽ കേസാണ്. അപ്പോൾ ഇവിടെ അബ്സല്യൂട്ട് സീറോ അല്ലാത്ത കേസിലെ എനർജി എക്സ്പ്രഷൻ എന്ന് പറയുന്നത് ഇതാണ്. ദിസ് എനർജി എക്സ്പ്രഷൻ. ആൻഡ് ഹിയർ dou by dou T, take derivative with respect to temperature. First term temperature illa, then second term here is pi kT square by EF0. ബാക്കിയെല്ലാം കോൺസ്റ്റൻസ് ആണ്. the only variable is t square അല്ലേ. t കൊണ്ടാണ് ഡെറിവേറ്റീവ് എടുക്കുന്നത്. t സ്ക്വയറിൻ്റെ ഡെറിവേറ്റീവ് 2t വരും. then this 3 by 5 NEF0, that's a common factor. സെക്കൻഡ് ടൈമിനെ മാത്രം ഡിഫറൻഷ്യേറ്റ് ചെയ്താൽ മതി. ആൻഡ് ദിസ് വിൽ ബി ഈക്വൽ ടു 3 by 5 NEF0, the common factor, into second term 5 by 12 pi k by EF0 the whole square, t square derivative 2t. And this will be equal to 1 by 2 n k pi square kt by EF0, and these constants together is lambda represented by lambda. ഈ കോൺസ്റ്റൻസ് എല്ലാം കൂടി ചേർത്ത് give the notation lambda, and CV is equal to lambda t. Lambda is this factor, that is CV is proportional to T, the specific heat contribution of metals at low temperature is proportional to the temperature in absolute scale. And this is the situation at low temperature. Electron gas in the case നമ്മൾ കാൽക്കുലേറ്റ് ചെയ്തത് ഫസ്റ്റ് an approximate value for Fermi temperature, then strongly degenerate Fermi-Dirac gas in the case E0 P0, then from the energy expression for low temperature in the case of Fermi-Dirac gas we found an expression for CV, and CV is found to be is directly proportional to temperature in absolute scale. And this is the electron gas in metals discussed using the theory of Fermi-Dirac gas.